Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be doing Unit 4, Lesson number 13 on compound interest. So what we've been doing throughout this entire unit is using both exponential functions and their inverses, logarithms, to solve a variety of problems. And one of the ones we want to dig a little bit deeper into today is how interest works, interest on both debt and interest on savings and investments and things like that. And specifically, we're going to take a look at what's known as compound interest. Now, this gets into some kind of very technical details about how banks work and how they sort of how they apply interest during different periods of time. So let's jump into that right now. Okay. A person invests 500 years in an account. 500 years. A person invests $500 in an account that earns a nominal yearly interest rate of 4%. Now, eventually, I'm going to explain what this term nominal interest rate means, but for right now, let's just roll with it. Let's just say I'm telling you you're getting a yearly rate of 4%. Letter A, how much would this investment be worth in 10 years if the compounding frequency, in other words, how often we apply the interest, was once per year? Show the calculation you use. This is something you should already know how to do, so go ahead and do it. All right, well, hopefully this is what you all said. I start with $500, and every year I'm going to get to multiply by 1.04, right? And I'm going to get it to do it 10 times. So this is my calculation. And what that ends up being, is 740.12214, etc. So after 10 years, that's worth $740.12. All right, easy, right? Easy. Now take a look at letter B, because this is where it starts to get new and different. If, on the other hand, the interest was applied 4 times per year, known as quarterly compounding, why would it not make sense to multiply by 1.04 each quarter? I want you to think about this for a minute. Well, it's very simple. If we multiply let's try that again. If we multiply by 1.04 4 times per year, we are getting, let's put it that way, we are getting much more than 4% interest per year. We're getting much more than 4% interest per year. You may even think, well, if I get 4% every quarter, 4 quarters, maybe I'm getting 16% per year. That's not actually true. All right, if you think back to our mindful percent manipulations, we could play around with it a little bit, but we'll eventually take a look. Let's take a look at C. If you were told, now this is an interesting question, if you were told an investment earned 4% per year, how much would you assume was earned per quarter, and why? Well, I think almost any person would say, well, if I'm getting, 4% per year, then I must be getting 1% per quarter. All right? And very simply, because there are 4 quarters in a year. Right? So you'd probably take that 4%, you'd divide it by 4, and you'd get 1%. Using your answer from part C, calculate how much the investment would be worth after 10 years of quarterly compounding. Take a look at that. Quarterly compounding. Show your calculation. Well, go ahead. See if you can figure out what this is, and then we'll take a look at it. All right. Well, whenever you apply interest, there's really only 2 things. What do you multiply by, and how many times do you multiply? Well, we're now taking that $500 and not multiplying it by 1.04, but multiplying by 1.01. Now we're not multiplying it 10 times, we're actually multiplying it 40 times, right? Why 40 times? Because we've got 10 years and we've got to multiply it by 4 to give me 40 quarters, right? Because we get to apply that at the end of the first quarter, second quarter, third quarter, fourth quarter. Then first quarter, second quarter, third quarter, fourth quarter. And if we actually put this calculation in, we find that it's equal to, can't get my pen to work, $744.43. By the way, notice, definitely more than this one, but not a lot more than that one, right? Not a lot more. And that will make sense as we move on through this lesson. Okay, but I really want you to think about what we just did there for a second, okay? We took a yearly rate, but we spread that yearly rate out amongst 4 quarters. But we got to apply it more often because instead of having to wait for an entire year, then multiply by 1.04, then wait for an entire year, multiply by 1.04, we would wait a quarter, multiply by 1.01, wait another quarter year, multiply by 1.01, another quarter year, etc. And it does change the amount of money we have. We have more money if we compound more often. All right, this is a very, very important problem. So pause the video now and write down anything you need to. Okay, I'm going to get rid of the text. Let's move on. Okay, the compound interest trade-off. The compound interest trade-off, right? For a shorter compounding period, more times per year, like quarterly or monthly or daily, right? For a shorter compounding period, we get to apply the interest more often, n times per year. So if we're compounding quarterly, n is 4. If we're compounding monthly, n is 12. If we're compounding daily, n is 365. But the interest rate will always be given as a percent per year. So we have to apply it at a lower rate. So we take our rate, whatever it is, and we divide by the number of times we compound to figure out what our rate is for that compounding period. So like in the last example, right, we took really not 4, but we took 0.04, divided it by 4, and we got 0.01, right? And then we got to multiply by 1.01. Okay, so this is the trade-off. Sure, we get to multiply more often, but using a smaller rate. And yet that trade-off is always a good thing. The more times we compound, the more money we will make. All right, I'm going to clear this out, and then let's see how much you understand about this. How much would $1,000 invested at a nominal 2% yearly rate, compounded monthly, be worth in 20 years? Show the calculations that lead to your answer. Some of you will already have picked up on what's going on here and can do this problem. So I'd like you to pause the video now and think about it. If you're completely lost, obviously I'm going to go through it, but think about it a bit. Okay. Now in the last problem, we had 4%, we divided by 4, we get 1%. Here, we're talking about compounding monthly, so I have to take that 2% and divide it by 12. But that's kind of ugly, right? If I do 2 divided by 12 on my calculator, I get 0.167%. Oh, that's kind of ugly. So here's what most people do. They're going to take that $1,000, and they're going to multiply it by 1 plus 0.02 divided by 12. And they're never actually going to work out what this is. Granted, it's 1.00167, but they're not going to even think about it. This is what we get to multiply by each month. Now notice, I did not do 1.02 divided by 12. I did not do 1.02 divided by 12. If I do that, it's actually going to be a decreasing exponential, and my money's going to be worth less, which would stink. Now, what do I raise it to? Well, how many times did I get to multiply? Well, there were 20 years, and I got to multiply 12 times per year. All right, so in my calculator, I want to put in 1,000 times 1 plus 0.02 divided by 12, all raised to the, what would that be, 240. I got to multiply 240 times over the span of 20 years because I'm doing it 12 times per year. And when I do all of that and work it out, again, something you must do on your calculator, can't do it in your head particularly, 1491328, closest to choice 2. All right. We're going to develop a very formal formula for this in just a moment, but pause the video now and write down anything you need to. Okay, let's clear out that text. And let's keep going. Exercise 3. For an investment with the following parameters, write a formula for the amount the investment is worth, A, after T years. So can you put this all into a formula? Now the nominal yearly rate is already in a decimal. All right, so if it's 4%, R is 0.04. If it's 10%, R is 0.1. All right, so what would this formula look like? Play around with it a bit. All right, well, here's the deal, right? What would we multiply by? Well, normally we'd multiply by 1 plus R. But now we have to divide that R out by n times a year. So this is my multiplier, right? This is what I multiply by. Of course, the P is what I start with. Now, how many times do I multiply by? Well, T is the number of years. But I'm doing n compounds per year. So I'm going to compound it n times t. So when n was 12, we got 12 times t, or in that case, t was 20 years. So here's my final formula. A of t is equal to the principal times 1 plus r divided by n, all raised to the n times t. And there it is. Now again, a lot of students don't tend to memorize this formula because they understand that trade-off, the trade-off between the compounding rate and the number of times we compound. But it is a famous formula. Open up any economics textbook or business textbook, you're going to see that one in there for compound interest. All right, pause the video now, write down anything you need to. Okay, clear out the text, and we'll use this a little bit more. So we keep seeing this term, nominal rate. And this can get a little confusing, okay? And I don't mean it to be too confusing. In fact, I think the New York State Regents totally brushes over this, but I want to talk about it a little bit. You see, in that first problem, I said I had a nominal yearly rate of 4%. And the reason I called it nominal is that a nominal rate is the rate that's reported on an account, but it's in name only. Okay, meaning that it really isn't the rate that you're getting per year. All right, you're actually kind of getting a different rate per year. But you use that nominal rate and then you divide it up by the number of compounds per year. Now what I want to contrast that with, though, is what's known as the effective rate. And that's the rate that you actually would get if you sort of put all those compounds together and you did it just once per year. All right, and this really gets back into our mindful percent manipulations. All right, the nominal rate and the effective rate are always very close together, and in fact they're identical in the case where you only compound once a year. But as soon as you have quarterly compounding, or as soon as you have monthly compounding, or what we'll eventually see, instantaneous compounding, then the effective rate is actually larger than the nominal rate. So let's do some calculations, see if we can actually figure out some effective yearly rates. Exercise 4. An investment with a nominal rate of 5% is compounded at different frequencies. All right. Give the effective yearly rate accurate to 2 decimal places for each of the following compound frequencies. Show your calculation. Well, all right. Let's talk about this. When we compound quarterly, what we're going to multiply by is 1 plus 0.05 divided by 4. But I'm going to do that every quarter, right? And that would actually be sort of my quarterly multiplier. But if I want to know how much I'm going to get in a year, I have to raise that to the 4th, right? I'm going to do 1, 2, 3, 4, and now I want to figure out this multiplier. So I'll put this all in my calculator, I'll multiply it out, and now I got to look at my cheat sheet, and I'll get 1.05094, etc. All right, so this is what I get to multiply by after a year. And that means I'm getting 5.09% effective interest. Now notice that's pretty close, right? You might say 5%, 5.09%, not a big difference. Then again, if you're working for a huge investment company and you're investing a couple $1 billion, I'm thinking the difference between 5% and roughly 5.1% is a lot of money. All right, let's take a look at what we get when we do it on a monthly basis. Again, here, if we want to think about what I'd multiply by per month, I would have this. This would be what I'd multiply by every month. And that means after a year, I would get to multiply by this. So I put that into my calculator, I evaluate, and I get 1.05116, etc. Notice, pretty close to what we got before, but a little bit larger. And in fact, we can say this one is getting me 5.12% interest. Interest is almost always given to you in terms of the nearest hundredth of a percent, So what we see is that compounding quarterly gave us a higher effective interest rate than compounding annually, but compounding monthly gave us a better interest rate than quarterly or yearly. Let's now do it to the nearest day. Now you might think, oh man, 4 times a year, 12 times a year, 365 times a year. Oh, that could be great. Maybe I'll get like 8% or something like that. So again, this is what I'd multiply out by per day. I raise it to the 365 and I'll figure out what I multiply by per year. And strangely enough, it's not that much bigger. 1.05126. So, if we kind of take this out, yeah, just a little bit bigger, but not much. All right, so these are the effective interest rates versus what the bank is telling us. And again, we could get into long discussions about why does a bank give you a nominal rate even though it's not the rate you're getting, etc., etc. But that would really kind of get into the conventions of the banking industry and economics and things like that. And we don't want to go there. Not at least right now. Okay? So pause the video now, write down anything you need to, and then we'll move on. All right, let's do it. Let's clear out the text and take a look at exercise 5, or not. Continuous compounding. That's the last thing we're going to do in this lesson. Now, this is a really, really interesting question. What would happen to this formula, right, if we compounded interest all the time? All the time. So not yearly, not quarterly or monthly or even daily, but every moment of all time. What we would get is we would get A equals PE to the RT. Literally, what we're having happen here is we're letting the number of compounds head to infinity. And that's a pretty tough idea, because then 1 plus r divided by n is getting closer and closer to 1, but this thing's getting larger and larger. And what we get is one of the most famous formulas. Sometimes this is known as the PERT formula. okay, the PERT formula. P times e to the RT. Now again, that R is already in decimal form, already a decimal, just like it was up here. Same R, all right? So when we compound interest all of the time, we now have P times e to the RT. There's our friend E again, all right? So I'm going to clear this text out, and then let's do a problem that involves continuous compounding. A person invests $350 in a bank account that promises a nominal rate of 2% continuously compounded. Write an equation for the amount this investment would be worth after t years. Well, as soon as we see this continuously compounded, then what we need to do is write down our PERT formula. A of t equals PE to the RT, and we just have to fill in the blanks. All right? The principal is $350. E is just E. And R in this case is 0.02 t. All right, that's it. That's the whole deal. Now letter B asks us, how much would the investment be worth after 20 years? Well, this is simply just asking, what is A of 20? Make sure you can do this on the calculator. Pause the video now and make sure you can substitute 20 into that function to get the proper amount. All right, well here it's really critical to use, I'm not going to open up the calculator right now, but to use that e to the x button that's above the ln button, all right? Because once you do that and you hit that e to the x, most modern calculators will then immediately put you into the exponent, where you'll just type in 0.02 times 20. You hit enter and you get $522.14. Continuous compounding is obviously the best compounding you can get. It's going to get you as much as you can. All right. Letter C, algebraically determine the time it will take for the investment to reach $400, round to the nearest tenth of a year. All right. So in other words, we want to know, ooh, that was beautiful, 350. We want to solve algebraically for this. All right, algebraically. Now we just did one of these in the last lesson. We had, I think, a law of cooling problem. And what we're going to be doing is we're going to be taking t, multiplying it by 0.02, exponentiating and multiplying by 350. So the first thing I'm going to do is get rid of this 350. Yeah, all right. That may turn out to be a nice decimal. It may not. It's like 8/7. It's not the prettiest thing. I'm just going to leave it like this. E to the 0.02t is equal to 400 divided by 350. Now, you could use either the log base 10 or the natural log. I'm going to use the natural log, and we'll again talk about why that is in a moment. But I'm going to just use that natural log, and the reason I'm going to do that is the natural log and e cancel. So I end up with 0.02t equals the natural log of 400 divided by 350, and then of course I can just divide both sides by 0.02, and that gives me 6.7 years. All right, letter D, what is the effective annual rate for this investment? So the nominal rate is 2%, but what's the effective rate, right? Before we would say, well, all right, this is what I multiply by. This is kind of tricky. What do we multiply by after a year? Well, think about it for a second. We have this 350 e to the 0.02t. We can use properties of exponents to rewrite this as e to the 0.02 all raised to the t. You see, this is what we're multiplying by every year. This is my yearly multiplier. So if I just simply take my calculator and evaluate e to the 0.02, I'll get 1.0202, etc. And that means I can kind of look at this and go, oh, my effective interest is 2.02%. And again, you look at that and you say 2%, 2.02%, not that much of a difference. And, with $350, it probably isn't that much of a difference. But, right, with a large amount of money, we want that continuous compounding. The other thing that's great about continuous compounding, and we haven't talked about this at all, is that when you compound on a yearly basis, literally you only get to add that interest at the end of the year. So really your bank account doesn't look like a classic exponential. It looks like a sort of a piecewise step function. Your money's holding, then it jumps up, then it's holding, then it jumps up, right? With continuous compounding, it truly does look like this nice, smooth, continuous exponential curve. And you can take your money out at any point in time and you don't worry about, oh man, I lost getting that interest at the end of the year, because you've earned interest at every moment in time. Okay, well, pause the video now and write down anything you need to. There's a lot on this slide. Okay, I'm going to clear out the text and then let's wrap it up. All right, so today we delved into the world of interest and finance, compounding quarterly, monthly, continuously. This can be a little bit confusing, but if we get away from the continuous compounding and the magical number e, then I really hope the other formula makes a lot of sense, this trade-off between getting to compound or multiply more often, but by a smaller number. All right. Thank you for joining me today for another Common Core Algebra 2 lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.